2017 RetinaNet focal laws for dense object detection. And this is the work from FB Facebook research group. And again, this is my personal reading notes. What I'm trying to do is to bring up the high-level summary for this paper. So let's first talk about the achievement. Why we read this paper and why this paper is important. It is because this is the first time that one-stage detector accuracy surpassed two-stage detectors. So first, RetinaNet is the one-stage detector. If you see the table below, you see there's a bunch of different works from one-stage detector and very famous one, YOLO and SSD. And then at that time, 2017-16, at that time frame, the dominant market for the accuracy is two-stage detector is RCNN family, faster RCN, fast RCNN, things like that. So this kind of regional proposal approach, even though they are slow, but they dominate the accuracy of the market. But RetinaNet comes out and then brings the accuracy like overpass the two-stage detector. So we're gonna learn why, what kind of techniques RetinaNet have to achieve this performance. So the problem for one-stage detector, why one-stage detector cannot surpass the accuracy for two-stage detector before, things like YOLO, SSD, why they are fast but they cannot surpass the accuracy is because of the class imbalance. And later we'll talk about the graphical problems that why class imbalance is a huge issue. It brings up mainly two drawbacks. The first one is training is inefficient, as most locations are easily negatives that contributes no useful signals. And later we will show you why, but just keep these 2 points in mind. The second is the easy negatives can overwhelm training and lead to degenerate model. Okay, so let's have a look about what is the difference between the one-stage detectors and two-stage detector. Let's have a look first to the right side, right? The two-stage detector here, and you see that there is this regional proposal family from RCNN, fast RCNN to faster RCNN. And they have a common point on their architecture. It's actually, they propose a regional first and then the classifier will work on top of that. Even though they have a different approach of proposing this region on the RCNN family, maybe they use selective search, and faster RCNN use the famous RPN, regional proposal network. However, the fundamental idea is, let's have a look on this diagram here. When there's an image comes in, the regional proposal based approach, they will they will have additional algorithm. It's a separate one. The additional algorithm will tell where has a high probability that might has object. So they can use a different segmentation approach. They can scan through the image and say, okay, here has something, because you see the segmentation change. Likely there might be some object. So there is additional algorithm will generate this before they go into the classifier. And this approach is actually reduce a lot of the potential proposal. So the segmentation algorithm, this regional proposal algorithm, they kind of generate around 2,000 blobs for possible regions. So they already reduce a huge amount of the potential area that might contain object, and that is a huge benefit. So they don't have that much class imbalance problem as a single stage detector we see on the left side now. So the single stage detector, for example, like YOLO, at the beginning, this is the slice of YOLO that you can see YOLO using this the anchor box to mount it on the different pixels of the image. So it's condensed down to a certain resolution, right? In this case, maybe from 224 times 224 down sampling to 3 by 3, and then you need to have an anchor box on each of these 3 by 3 positions, and depending on that anchor box, they could have, in this case, right, there is a two anchor box, like this first one and the second one, and then there might be different aspect ratio. So it depends on the algorithm design. You might have a multiple anchor boxes at one positions. So in this case, that yes, it's a good position. But how about this one? So if we had generate also 5 anchor boxes and with two different aspect ratios, so we have 10 combinations generating this pixel here. However, there's nothing. So for the problem of one stage detector, if you see down slides before, in one image, there is a lot of areas contains like no useful information. So your classifier, your model will learn, okay, here has a lot of negative, we call easy negative example, because I just need to say, hey, here has nothing, and I'm correct. So even though it is easy, so my loss functions will generate very minor values. However, there are a lot of positions that generate this kind of easy information. And if you have a trivial fractions of scores inside your loss functions, you don't care at the beginning. But if you have a huge amount of this small fraction of scores, in the end, that will overwhelm the whole models. So let's take a look of this is how many dense proposal would generate from different model. You see from YOLO V1 is only 98 boxes generate, so it feels okay. But start from YOLO V2, you see there's a 1K, and overfit has a 1 to 2K. 2K is the same numbers as two-stage detectors, like 2000 blobs per possible region. And now from SSD, it's go from another order, and then RetinaNet has 100K, means 100,000 bounding box would generate for a single image. And then this 100,000 K maybe only contain one object or two objects, or let's say 10 objects, but you still have the total number of the area that contains nothing. So this is exactly the problems. In one image, there has multiple easy negative examples, and that might cause the problem for your model. So another view angles, right, from the YOLO V4 papers I talked about before, and there's a link on the description below to the papers. We are talking about YOLO V4 there, but I'm gonna borrow that image again here. So this is the architecture of a common object detectors, right? And then you can see here separate into one-stage detector and two-stage detectors. And in the one-stage detector is kind of similar like a simplified pipeline. You have input, you have your backbone. The backbone in RetinaNet in this case is the Resonate. So there is a lot of papers they are using the backbone from Resonate. So Resonate is a very important architectures, and I have another video also for Resonate. If you are not familiar with that, check the description below. And then we pass through another layers we call NEC. So NEC, what NEC do is basically combine the segmentic informations from the backbone. So we know that from the low semantic informations from the low layers to the high semantic informations from the later layers, that they can be combined and can be useful for the classifier, for the detector in the future. So the NEC in this paper in in the RetinaNet paper, they are using FPN, which everybody also using FPN during that time. So I have another video also for FPN. FPN is a very important techniques. You have to check it out for the descriptions below. There is a link, and then you go to the one-stage detector head, which is this dense prediction. So you can see here has a lot of different boxes generated. This is called dense approach because each pixels you're gonna generate a bunch of different anchor box and also the aspect ratios combination, so you have a very dense boxes around on your final detectors. However, it's the same pipeline as the one-stage detector. If you look at the two-stage detector, what is different is just because they don't use this dense prediction approach. Instead, they have this regional proposal approach. They're gonna propose some regions, and then you will do the detection afterwards. So that regions reduce a lot of the problems. So remember again, what is the problem we have? We have the class imbalance problem. Why? Because in dense predictions, we have every pixel position, we need to generate some anchor boxes and aspect ratio, which is a lot of like negative, easy information. However, in a two-stage detector, we have this regional proposal approach. They will filter out a lot of non-useful information. So we only have useful information in the end, so we generate the result. And that is the reason why two-stage detectors dominate during that time frame, 2017, for the accuracy on object detectors. So now, RetinaNet, they propose a new things. The previous thing we talk about RetinaNet is not new, because what we talk about, the first RetinaNet is using the backbone as ResNet 101. Second, it's using FPN, which is all not new stuff, okay? The new stuff is a new loss function. It's called focal loss, and that is exactly the name of this paper is called focal loss. And let's have a look why they propose this. So one thing to keep in mind, I like the RetinaNet, this paper, is because they are starting from the angle of first principle. They're using just a purely the beauty of math to achieve this work. So if we see the cross entropy, because for this classified problems, the loss functions, we are using cross entropy. And if you have a look here, so this diagram is just telling you that if, let's say if there's a dog, and then if my classifier say, okay, my object detector say, okay, I'm detect now like 90%, 0.9, it's a dog. So am I right? I'm right, but I'm not quite right. I'm still generate fractions of loss functions. In this case, it will be 0.1. And then if my classifier said, okay, I think that's 0.1, that's 10%, it's a dog. So I'm pretty wrong, right? So my loss function will be huge. And that's the beauty of the cross entropy math behind that. You know that if you are pretty correct, your loss function will be low. If you are really if you are 100% correct, then your loss will be 0. However, if you consider the problem we talked about before, there is a huge imbalance of the problems. So if we have 100K easy example compared to 100 hard example, and if you times these numbers, even though at the beginning you think, okay, this is just 0.1 and this is 2.3, of course, my model will try to learn hard on this problem. However, the truth is, if you have a huge class imbalance problem, even the small amount of loss will overwhelm in the end. If you times 10,000, if you times 100,000 for this loss, and then if you times 100 on the problem of the hard problem, and in the end, you see the easy examples even 40 times bigger than the problem here. So now we need to think about just trying to mimic what those researchers trying to do at that times, right? If you have this curve, and now you want to even reduce this contributions, because you know anyway this easy example will be a huge amount. And what we're trying to do is we're trying to focus this more. We're trying to focus less this on the easy example. So what we can do is can we somehow even press this curve let's say, can I press this value even down to 0? Is that possible? And then that is exactly the focal loss. So if you see the formula here, this part is just cross entropy, but they have this modulating part, which is 1 minus p. And you don't need to understand deeply about this formula. What does it mean? You just have a look on this, the graph output. So the blue line is the previous cross entropy, and the green line is the new loss function they call focal loss. And the difference is the focal loss is exactly achieve what we want to have. We want to press this curve even down. Okay, so if you see here the same problem before, if the 90% chance I say this is a dog, I generate 0.1 as a loss. In the new focal loss, I will only generate 0.01. So I'm even pressed down one order lower values by using these terms. I just add, from math perspective, right? I add the simple modulating terms, which is this 1 minus p, and then with the power of r. This r is called the focus parameters. Let's have a look here. So there is a two parts here. One is this 1 minus r, is called modulating factors 1 minus r, and then there is a power of 1 minus p, and then there's r called focusing parameters. So they have tried some application starting in these papers. They use in between 0 to 5. In this case, you are looking at r equal to 1, and they found out that r equal to 2 works the best in their ablation study. So now you can see this most important diagrams that you will see on the RetinaNet all the times. That you have your original, which is cross entropy. Cross entropy is just r minus 1, because cross entropy is just the special term in the r minus 1. So this is kind of very beautiful math terms that you have a new modulating factors. However, if you add some, if in some special case you are converge into the cross entropy, right? So in this blue line is just a cross entropy, and what focal loss is trying to do is to reduce those easy part. So the idea of focal loss is just have a math behind, and then to press this curve down to as low as possible. So if you see if r equal to 5, then you can press really low here. However, you need to also keep in mind, if you put a bigger r here, if you see the left here, you also press down the loss you're trying to learn before. So you kind of only want to press down here in these easy examples, but you want to keep here because this is something you want to learn. You classify wrong here, you want to learn, your model want to learn here, so you better keep this on the original position as close as possible. So you see here is just a little bit like 10%, or like 0.2 here, and here is the order of 1, right? So this is kind of the trade-off you need to take into account, and that is why it's not necessary r is the bigger is the better. So in the end they say r equal to 2, which is this purple line here, they think is better, because if you feel about this, the hard problem is still maintained there, but the difficult problem is pressed down a lot. So this slide is just the most important slide, and that is the beauty of the focal loss here. And now we're gonna shortly talk about what is actually RetinaNet, right? So we talk about RetinaNet is just a combination of 3 things. It's just ResNet 101 as a backbone, FPN as a neck, focal loss, that's a new thing. The previous 2 things, old stuff. The focal loss as the loss functions. So it's just a simple architecture here. Again, we just recap. ResNet here, have a neck here combined with segmentic information from different layers using the FPN, okay? And then pass through the the detector, the head. One is for the classifier, one is for the regressions of make sure your bounding box's location is right. So I think this is the final slides. We talk about the performance of the RetinaNet. So you can see that a bunch of different other one-stage detectors here are, for example, the B is SSD, and they are fast, but the accuracy is low. And then you can see the RetinaNet 50, which is of course using ResNet 50 as a backbone. They are fast, but the accuracy is still not that high as if they using the ResNet 101 as a backbone, which they call RetinaNet 101 here. And also one very important thing is why they using FPN, right? Because FPN can really helps a lot of detecting the small object. Before, the problem of YOLO and SSD even, if you have a look in this FPN paper video I did, you can see YOLO is not using FPN at all at the beginning, so they have a very bad performance on the small object detections. However, SSD, they're using some kind of the idea of FPN, but it's not there yet. So you better check out that video. So FPN really helps also to detect the small objects, and yeah, you can have a look at that videos. So that's all from what I want to share on these papers. So the most important thing is the focal loss of this RetinaNet paper. The focal loss is just adding a terms. They contains two factors. One is modulating factors, and the second is the focusing parameter. And using these mathematic terms to build up this beautiful math behind to press down the easy example here, and then to still maintain the hard example values there to make sure our model, when they try to learn this easy example, don't cause too much focus when they are learning, but they focus on the hard problem they really try to learn. That's all for this paper. Thank you everybody.